Hi guys, my name's Astronaut Mars, and for the past few days I've been wondering about the power rule. The power rule states that given you have a function f of x is equal to x to the power of n, the derivative of that function is equal to n times x raised to the power of n minus 1. And the way we can prove this is by using a limit statement. And before we do that, I think it's important that we understand the definition of a derivative so we know how we're deriving our equations. So what exactly is a derivative? A derivative is just the slope at a single point, otherwise known as the instantaneous rate of change. Now, you're probably already familiar with the average slope formula, which is you're basically comparing two different points to each other and finding the average, the rate of change between them. And this is the one we're probably all familiar with through middle school, and it's used to approximate the slope between two different points. But what if you wanted to find the slope at just one single point? Without derivatives, you could approximate this by using the slope formula with two extremely close values, but ultimately this is just an approximation. However, we can use a modified version of this slope formula that uses the same concept as taking two extremely close values. And the way we format this limit statement is by saying the limit of f x plus h minus f of x all over h as h approaches 0. And by using some very clever substitutions, we can solve for this limit. Right now, we can't plug in h equals 0 directly because our denominator would be 0, and we can't have that. So we're going to have to find a way to remove h from the denominator. So now let's put this limit statement to the test. Suppose we have function f of x is equal to x to the power of n. And we use our good old limit statement that we used previously and plug in our values. So our fx plus h in this case is going to be x plus h to the power of n. And we subtract our initial function all over h. So what do we do from here? We can't expand out this x plus h to the nth term. So we're going to have to approach this limit statement in a different fashion. And the way we can approach this problem is by looking at the numerator as the difference of two numbers raised to the nth power. And I'm going to explain what that means in a second. So I'm just going to erase all of this for just a quick second. So let's take a squared minus b squared, for example. So you have a squared minus b squared. You can factor this equation into two factors, a minus b and a plus b. And if you multiply all these terms out, it'll result in the exact same equation as the original equation. Now what if you had a cubed minus b cubed? You can again factor out an a minus b, and you know there has to be an a squared and a b squared term in there. But we also need to include an additional ab term in order to ensure that the second equation is the exact same. The second expression is the exact same as the first expression. Now, what if we had a to the power of 5 minus b to the power of 5? You'd once again have an a minus b term, and an a to the power of 4 and b to the power of 4 term, but you also need to include an a cubed b plus a squared b squared plus ab cubed plus b to the power 4 term. And let's also look at how many terms are in each of the second factor. So in our a squared minus b squared example, we had 2 different terms in the second factor. In our cubed example, we had 3 terms in the second factor. And in our a to the power 5th minus b to the power 5th example, we had 1, 2, 3, 4, 5 different terms in our second parentheses. And using all of this combined knowledge, we can reasonably say that given a to the power of n minus b to the power of n, you can factor it out such that the first term is a minus b, the first factor is a minus b, and the second factor will be a to the power of n minus 1 plus a to the power of n minus 2 times b plus everything in between, all until you get to b to the power of n minus 1. And in this second factor for raised to the nth power, we can say that there are n terms in this second factor, and that's important to know. And it's a bit like Pascal's triangle, but without the coefficients. Now, let's go back to our initial limit statement. So we have the limit as h approaches 0, x plus h to the power of n minus x to the power of n all over h. That's our initial limit statement. In this case, so let's remember our a to the power of n minus b to the power of n that we were discussing. Let x to the power of h be our a term, and let x be our b term. So now that we know that, we can factor this out such that we have our a minus b, which will be x plus h minus x, multiplied by x plus h to raised to n minus 1 plus x plus h raised to n minus 2 times x, plus so on and so forth until we eventually get to x raised to n minus 1. And this is all divided by h. Now, we can further simplify this first factor, because this first factor, we can cancel out the x's, so all we would get is h in the first factor. And since we only have h being multiplied by another factor on the numerator, and we have an h at the denominator, we can cancel out the h on the numerator and the h on the denominator, which would leave us with this limit statement. And I'll just leave out some of the middle terms as to leave us some space. And as you can see, from here we can just directly substitute for h, because we're no longer going to get an undefined answer now that h is no longer in the denominator. And so we left off at the limit of h approaches 0, x plus h, n minus 1, plus, and I'll include a couple of extra terms just so it's clear what we're doing. And so now that h is no longer in the denominator, we can safely plug in h equals 0 without getting an undefined answer. So from here, we can drop the limit statement, and we can just plug in h equals 0. And x plus h is just equal to x plus 0 now. So all x plus h terms are just going to be equal to x plus 0, and x plus 0 is just x. So every single x plus h term will just be replaced with an x. So we have x to the power of n minus 1 plus x to the power of n minus 2 times x, so on and so forth, plus x times x to the power of n minus 2 plus x to the power of n minus 1. And all these middle terms are going to be different variations of, as one term's exponent is decreasing, the other term's exponent is increasing. So these middle terms are going to be x to the power of n minus 3 times x squared, x to the power of n minus 4 times x cubed, so on and so forth. And what you realize is when we multiply all these terms together, when you're multiplying these two different exponents with the same base, you add the exponents together. And so what you notice is that all of these are just equal to x to the power of n minus 1 plus x to the power of n minus 1, so on and so forth, plus x to the power of n minus 1 plus x to the power of n minus 1. Now, remember what we previously said about the amount of terms in that second factor of a to the power of n minus b to the power of n? The amount of terms in that second factor is n amount of terms. There are n amount of terms in that second factor. And we are essentially just adding up the same numbers n amount of times, which is otherwise just multiplying that number by n. So we end up, this expression will end up equaling n times x to the power of n minus 1. And so using the definition of a derivative, we can prove that the slope at any given point in the function x to the power of n is going to equal nx to the power of n minus 1. Thank you for watching.